Perfect. So thank you very much for the effort in joining us on Friday
okay. It's a very civil topic.
afternoon. So I'm going to accept the other participants, and I think we can wait just a couple of minutes and then we start.
No, that's okay. Very happy.
Many people are joining us.
Good. We've currently got quite a nice sunset going on here, and I'm actually quite happy to be giving a talk now because I'll finish a little after sunset, and there's a forecast for some auroras tonight, so I may even get to see an aurora towards the end of my talk. Good fun.
Nice. I think we can. I think we can start. So, good morning, everyone, and welcome to our IPARCOS seminars. Today it's my pleasure to introduce Dr. Jonah Gannon. Jonah earned his PhD in 2022 from Swinburne University of Technology and is currently working as an astrophysicist research fellow at the same institution. His research focuses on galaxy formation and evolution, with particular interest in dwarf and ultra-diffuse galaxies that mark stellar populations. His work has contributed significantly to our understanding of galactic dynamics and low-surface brightening imaging. Jonah has extensively observational experience, having served as a lead observer on major instruments such as Keck and VLT observatories. He has been recognized with several prestigious awards, including the 2023 Early Career Fellowship from the Instituto de Astrofísica de Canarias and the co-investigator role in the 2022 Spanish Plan National Grant. Today, Jonah will present his latest research on the building evidence that some ultra-diffuse galaxies are phase galaxies. So thank you very much, Jonah. The floor is yours.
Thank you very much for that wonderful, wonderful intro. So it's my great pleasure to be joining you here today from Australia. As I said, the sun is setting. I work at Swinburne University of Technology. And in particular, a lot of the work I'm going to be presenting today is part of the Agate collaboration. So if you haven't heard of the Agate collaboration, I don't blame you. Some people like to pronounce it Agate. It stands for Analysis of Galaxies at the Extremes. It's a little collaboration we've got going to study some of the most extreme cases of galaxy formation we see in the universe to try and understand how galaxies form and how they evolve. The main researchers working as part of this collaboration are listed down below. Anna Ferry-Matau is at the IAC in the Canary Islands, and I visit her quite regularly. I'm hosted here at Swinburne by Jean Brodie and Duncan Forbes. And of course, a lot of the work I'll be presenting here today are the work of our PhD students, Maria Buzo, Lydia Hake, and Arsene Levitsky. So if you don't know what an ultra-diffuse galaxy is, that's okay. This is a plot of an ultra-diffuse galaxy, just to give you some idea as to what we're going to be talking about today. So this is a nice deep image of an ultra-diffuse galaxy, much deeper than the other two. And the point of this image is simply to show you that this galaxy, even though it has roughly the same number of stars as the little dwarf elliptical, these stars are spread out over a much larger area. And in the end, if you measure a half-light radius, it tends to be much more like the disk of a more massive galaxy. And immediately from looking at this image, we can start to think about a few of the ideas as to how this galaxy forms. So many of the ideas in the literature suggest you just get a normal, smaller dwarf elliptical galaxy, and through some mechanism, strong stellar feedback, tidal interactions, high halo spins, you can puff up the stars in this galaxy and form the ultra-diffuse galaxy we see today. But there was another idea that was initially posited when we first saw these galaxies, and that was because of their large size, they might actually have quite massive dark matter halos. Maybe not quite as large as an Andromeda galaxy, but something a bit more like the Large Magellanic Cloud M33, a few orders of magnitude more than we'd expect for their stellar mass. And so we'd actually think about these as kind of like a failed dark matter halo. It's a dark matter halo that hasn't been expected, but it hasn't formed the expected stellar mass, given its high halo mass. And that's going to be the focus of this talk, this second formation pathway, and the evidence that's been building that we may actually have this happening in the universe. So just to try and get you interested as to why we may want to study these galaxies beyond that, this is a plot that gets made whenever a new type of galaxy is discovered. It's simply a plot of the halo mass of the environment you find the galaxy in versus the number of galaxies you find in that environment. You can fit a line to it and work out the slope of that line. And the reason you do this is just because the slope will tell you if environment plays a major role in helping to form these galaxies. So if this slope was well above 1, you would find the galaxies are much more strongly biased to being in clusters, and so clusters are probably doing something to help form the galaxies. If the slope is much less than 1, then what you're showing is you're much more likely to find the galaxies in the field or in groups, and so clusters might be doing something to destroy the galaxies. But the reason it's interesting for us today is just simply the sheer number of galaxies we find across all environments of the universe. You'll see that the slope is very near 1, which suggests that environment may not play a huge role in forming these galaxies. But if we just take one example, in the most massive environment, the Hubble Frontier Field, Able 2744 at a redshift of about 0.3, it's a JWST early science field for the GLASS collaboration. It has tens of thousands of galaxies. Perhaps a good estimate of the number of galaxies is 30 to 40,000. And work of a collaborator of mine, Steve Janssens, found 1,350 ultra-diffuse galaxies, which means that roughly 5%, or 1 in 20, of all of the galaxies in this massive cluster are ultra-diffuse galaxies. If you go right down to the other end of the spectrum, in our own local group, we have of order 100 galaxies. You find that 4 or 5 of them are ultra-diffuse galaxies, depending on your definition. So again, you find that roughly 5% of the galaxies are ultra-diffuse. And this actually holds across all the across all environments, where we really think that by previously missing out on observing these low surface brightness galaxies, we've been missing out on observing 5% of all the galaxies in the universe. One thing I do want to point out, though, is that when this definition was first posited, it was quite a broad definition and didn't have strong science motivation. And because of this, it takes in a very broad range of objects that we would consider ultra-diffuse. And to help you understand this, I'm just showing 3 examples here. On the left, I've got this galaxy AGC 103435. It's got a stellar mass of a few by 10 to the 7. It's got 2 globular clusters that have been circled in red from Hubble Space Telescope imaging. You'll see it's in the field. It's very blue and irregular. It's got star-forming clumps. It's got actually a very massive H1 disk. It's contrasted quite nicely by this galaxy in the middle. This is PUDG R15. It's a Perseus cluster ultra-diffuse galaxy. It's got a stellar mass of a few by 10 to the 8. It's got 13 globular clusters that have been revealed by Hubble Space Telescope imaging. Obviously, it's in one of the most massive local clusters, the Perseus cluster. And instead of being blue and irregular, you'll see it's actually red and smooth and has a very different morphology. And finally, we've got this last galaxy, NGC 5846 UDG1. Some people also call this MATLAS 2019. It also has a stellar mass of a few by 10 to the 8. It's got 54 globular clusters, all these little dots here, that have been revealed by Hubble Space Telescope imaging, and it's in a group. So what we've really got here is 3 galaxies of very, very similar stellar mass, same order of magnitude. There are certainly examples of H1-rich irregular field UDGs with a mass of about 10 to the 8, but very, very different globular cluster richnesses. They have very different globular cluster richnesses all the way up to 54, which is about a fifth the number of globular clusters our own Milky Way hosts in a galaxy that is 100 times less massive in stars. And this is interesting to us because astronomers can be inherently lazy, and when you're inherently lazy, You get a new class of galaxy and you just go, okay, let's estimate a mass for it in the easiest way possible. And so for these ultra-diffuse galaxies, there are two really easy ways of trying to estimate a halo mass for them. You have the stellar mass-halo mass relationship, and you have the globular cluster number halo mass relationship. So here I'm plotting the stellar mass-halo mass relationship from a review of Wexler and Tinker et al. 2018. The slight caveat here is that they've divided the y-axis through by the stellar to halo mass ratio. So divided it through by halo mass to get the stellar to halo mass ratio. You'll see that it's got this characteristic U shape, no matter which author you believe in deriving it, where star formation is most efficient in Milky Way mass halos, and then is suppressed by AGN feedback in more massive halos and by stellar feedback in less massive halos. And so what you take away from this to estimate a halo mass is that because all the galaxies I've just shown you have broadly similar stellar masses, you might expect them to all have broadly similar halo masses. If we then look at the globular cluster number halo mass relationship, number of globular clusters, the total halo mass of the environment, this plot is taken from a paper by Burkett and Forbes 2020. You'll see that over many orders of magnitude, if you simply count the number of globular clusters you get in the system, you actually get a very good estimate for the total halo mass of that system. And so if we were to use UDGs in this relationship, we'd actually say that their large range of globular cluster numbers is going to imply a very large range of halo masses. And clearly, both of these conclusions can't be true. UDGs can't all have the same stellar masses, and so the same halo masses, but also all have a large range of globular cluster numbers and a large range of halo masses. It doesn't agree. And so in trying to work out what the answer to this question was, I've been doing a lot of spectroscopy of ultra-diffuse galaxies, and the literature started to get quite disjoint. Lots of people had been contributing to it. So in order to make it easier for everyone, I've created a catalogue of ultra-diffuse galaxy spectroscopic properties. So in order to be included in my database, I would like a galaxy that has a half-light radius above 1.5 kiloparsecs and an average V-band surface brightness that is fainter than 24.7 mag square arc second. Don't worry about these first two so much. This is simply saying that they're an ultra-diffuse galaxy. It's the definition that I've chosen. But the third one's the important one. I really want these galaxies to have spectroscopic stellar velocity dispersion, globular cluster velocity dispersion, or spectroscopic stellar population information. And currently, I think my catalogue has 33 galaxies meeting this criteria. If you'd like to use it, there's a QR code there, there's a link down the bottom, and there's a paper published on arXiv describing the catalogue. I should say that this work really isn't my own. It's the work of a lot of good people in the literature. And if you're going to use the catalogue, please do try to cite the people who've contributed to it. It's listed in the catalogue, and I've tried to make it as easy for you as possible. I do want to be really upfront and say that this catalogue is by no means complete, and that there are a number of known biases in this catalogue that we're going to use to investigate this question. So here I'm plotting this spectroscopic catalogue in blue and comparing to a photometric sample that our group has analysed for SED fitting in orange. And UDGs with spectroscopy, in comparison to the photometric samples we're seeing, we tend to be studying them in clusters. They tend to be brighter. They tend to be much higher stellar mass, larger. They're slightly rounder. They tend to be more globular cluster rich. They're older. And quite interestingly, actually, we're actually seeing a more diverse metallicity spread in ultra-diffuse galaxies we're studying with spectroscopy than those we're fitting with SED fitting. So let's go back to this original question. Do ultra-diffuse galaxies follow the stellar mass, halo mass, or globular cluster number, halo mass relationship? So as an observer, this is an observer's proxy for the stellar mass, halo mass relationship that we'd like to try and use. So here we're plotting the dynamical mass to light ratio versus the dynamical mass. The dynamical mass is kind of a proxy for our halo mass, and the luminosity is kind of a proxy for our stellar mass. You'll see that you still get this nice U-shaped relationship. Here it's been inverted because the dynamical mass, our proxy for the halo mass, is now on the top rather than the bottom of our fraction on the y-axis. So I established the relationship with a whole bunch of non-UDGs in black, and then plot masses from UDGs coming from the velocity dispersion of their stars in blue, or coming from the velocity dispersion of their globular cluster system in red. And I think it's just immediately apparent in this relationship that ultra-diffuse galaxies do not seem to be following the same U-shaped relationship that we're seeing for non-ultra-diffuse galaxies. But perhaps this means that we don't expect them to follow the stellar mass-halo mass relationship. Just to investigate this a little further, I've created this plot. So when I'm plotting dynamical masses in the previous plot, I'm plotting virial mass estimators. So for those of you who are not aware, you can get a mass for a galaxy by measuring a velocity dispersion, and the dynamical mass will go as the velocity dispersion squared times the half-light radius. There are different ways of deriving it. On the previous plot, I was using a famous formula by Wolf et al. 2010. So to investigate whether or not it's the velocity dispersions or the large half-light radii of these galaxies that are driving their large dynamical masses, we have this plot. So we've got the velocity dispersion of the galaxy as a function of its stellar mass. Again, non-UDGs are plotted in black. And I think it's quite apparent from this plot that most of the UDGs, particularly with stellar velocity dispersions, seem to follow the relationship for non-UDGs. They actually have quite normal velocity dispersions. What's happening is that a lot of their extra mass is just being driven by their large half-light radius. The same doesn't seem to be true from globular cluster velocity dispersions. They seem to have much higher velocity dispersions. And we're still investigating this as a field. I think there's some chance that these high globular cluster velocity dispersions are being driven by interlopers in the data that are very hard to remove because the galaxies are in clusters. So you're never quite sure whether the globular cluster you're measuring is actually associated with your dwarf galaxy or is just projected near it. And so when returning to this plot to talk about this a little further, I think I'm actually going to remove the globular cluster velocity dispersions for the rest of this talk because they do seem to be very odd for the stellar masses of the galaxies in which they're being measured. And they're much more indicative of a far, far more massive galaxy. But if we start to think about the aperture effects at play in this plot, I think it actually starts to become very important. So because this is an observer's proxy for the stellar mass-halo mass relationship, we're not measuring the total stellar mass and the total halo mass. We're just measuring it within some radius. And because ultra-diffuse galaxies are, by definition, larger at the same radius than similar mass dwarf galaxies, you actually end up taking more of the dark matter halo in your mass measurement in. And so you end up with more dark matter for the same stellar mass by default, which leads to this dark matter domination that may be seen for some galaxies. And so if you were to take this aperture effect in place, you might have something like a shift like this, a 50% increase in the dynamical mass for non-UDGs. But the really important thing to take away from this is that if you do this shift, you still end up with much larger scatter in the ultra-diffuse galaxies we're measuring than in the relationship for non-UDGs. No matter how you include aperture effects in this plot, you can't get the ultra-diffuse galaxy data to match up with the expectation of our observer's stellar mass-halo mass relationship. So I really am not sure it's appropriate to say that ultra-diffuse galaxies do follow this stellar mass-halo mass relationship. So if they don't follow the stellar mass-halo mass relationship, then I think there's a natural question as to whether or not they follow the globular cluster number halo mass relationship. So this is the observer's proxy for the globular cluster number halo mass relationship. Globular cluster number is on the y-axis, and again, instead of halo mass, we're using dynamical mass on the x-axis. And here you can have the very simple assumption that if globular cluster numbers trace halo mass, as you increase the globular cluster number, you probably also expect to increase the dark matter or the mass within the central radii. And so we've got a whole bunch of points for non-UDGs in gray, with the best fit line to the points from this catalogue of Harris et al. As the black line. And we've got dynamical mass measurements for UDG stellar velocity dispersions in blue. And I already think there's much better agreement with this plot than there was at all for our observer's proxy of the stellar mass-halo mass relationship. So I'm inclined to say that UDGs are more likely to follow the globular cluster number halo mass relationship than the stellar mass-halo mass relationship. Yeah, maybe a little bit, well, when I look at this plot, there's a little bit of me that asks, why do all of these galaxies lie off to one side? And there's actually some natural explanations if you start to think about dark matter halo profiles. So it could just be observational uncertainty in the data, but something that does happen in this plot is that the halo profile shape will make a difference in where galaxies lie in this plot. So at fixed halo mass, if you, by definition, have less dynamical mass in the central regions, you're residing in a chord dark matter profile. And so if ultra-diffuse galaxies, these big puffy dwarfs, have some of the most diffuse stellar components, I don't think it's insane to say that they may also have some of the most diffuse dark matter halos and have these chord profiles in the middle. You can also make a similar argument with concentration parameter, but that starts to get a little bit more complex. And so I'll spare you that explanation. And so one of the things we wanted to try and do is see if we could get a halo mass estimate, even if very crude, from our globular cluster number estimates. Not from our globular cluster number estimate, sorry, from our dynamical mass measurements, to see if we could get them to agree with our globular cluster number measurements as a second confirmation of these massive dark matter halos. And so to do this, we get our single dynamical mass measurement, we make an assumption of a dark matter profile, either cuspian FW or chord, and we extrapolate it out to get a total halo mass measurement. So we just fit straight through one mass point to see if we can get a total halo mass. And because we have this expectation that ultra-diffuse galaxies follow the globular cluster number halo mass relationship from the arguments I've made previously, we try and get the halo mass we get from this extrapolation to match the halo mass we get from the globular cluster system. This is a plot showing that. We've focused on ultra-diffuse galaxies in my catalogue with more than 20 globular clusters, just so that we have an accurate estimate of their total dark matter halo mass coming from their globular cluster counts. And then we do this fitting. So if you fit with a cusp, you find that almost all of the total dark matter halo mass estimates you get from extrapolating out of dynamical mass measurements end up much less massive than you'd expect, given their large globular cluster system. Alternatively, if you do the same process with a core, though, you find much better agreement, which for me is just the second bit of evidence that we actually might expect these galaxies to have a large dark matter core. These are arguments that were presented in Forbes and Gannon, if you'd like to have a look at the paper. I should also say, and some of you may have noticed, there's this orange point here in both plots. This is a plot for the galaxy, or for the ultra-diffuse galaxy Dragonfly 44. It's actually got a resolved velocity profile, which allows fitting of a dark matter halo. They also assumed a cuspy dark matter halo and found it lied here. Whereas if you assume a core, it lies here in much better agreement with the expectation of its globular cluster numbers. So I really do think we're starting to build up evidence that these galaxies may have a dark matter core. If you then take these total halo mass estimates you get from the dynamics and put it on the stellar mass halo mass relationship, you get this plot here. So you'll immediately see that one galaxy probably has its halo mass overestimated by assuming a dark matter core. Very simply, this can be fixed just by assuming a cusp. It'll become much less massive. So perhaps this isn't true for all galaxies. But there are three main things I want you to take away from this plot. So this is the stellar mass halo mass relationship. Now I'm not dividing through by the halo mass on the y-axis, but just purely plotting stellar masses. I have canonical stellar mass halo mass relationships in brown and in gray. I have simulated ultra-diffuse galaxies from the Nihao and Fire simulations in purple and in orange. I have my halo mass estimates in blue that I'm deriving from the dynamics of the stars. And I have halo mass estimates from the rotation curves of the H1 system in green, coming from field UGGs. So the first thing I want you to take away from this plot is that by and large, almost all simulated ultra-diffuse galaxies simply follow the stellar mass halo mass relationship. There's very little scatter in these two simulations in ultra-diffuse galaxy halo masses. This, of course, doesn't seem to be what we're seeing observationally, where there's a much larger scatter in this relationship. We see some ultra-diffuse galaxies at very low halo masses for their stellar mass, and we're seeing this population at very high halo masses for the stellar mass. And so those with low halo masses for their stellar mass are actually somewhat easier to explain. If you have tidal stripping, you preferentially remove the outskirts of your dark matter halo first, and this will lead to lower halo masses for your stellar mass. What's much more difficult to theoretically explain are these ultra-diffuse galaxies lying off the right of this relationship in this very high halo mass for their stellar mass regime. The only real way that we can theoretically do this is by simply quenching a dark matter halo. You get something forming at very high redshift, you stop it forming stars at redshift 2-ish, and just continue on for the rest of the age of the universe, having it passively evolve. And so there's actually this little caveat here, where when I say ultra-diffuse galaxies aren't following the stellar mass halo mass relationship, I really should be saying at redshift 0. And the reason I need to add the at redshift 0 is because the stellar mass-halo mass relationship is known to evolve. So this is also from the review of Wexler and Tinker et al. 2018, plotting the stellar to halo mass ratio versus the halo mass. And you'll see that at very high redshift, the first dark matter halos collapse, and dark matter starts merging. And very quickly, you get a growth from the dark matter halo, which significantly outstrips the ability of the galaxy hosted in that halo to form stars. And so things become much more dark matter dominated very quickly. And this proceeds all the way up to a redshift of about 4. And between redshift 4 and 2, there's this stalling. Galaxies start to form stars almost as efficiently as the halo can accrete dark matter. Redshift 2 is this famous peak of cosmic star formation in the universe, the Mandow and Dickinson plot. And the stellar mass-halo mass relationship evolves into what we see it today, becoming slightly less dark matter dominated. And so when I've been saying that this population of ultra-diffuse galaxies may not obey the stellar mass-halo mass relationship at redshift 0, it's not actually as clear that this should be the same case at high redshift. If I put them on this plot, something that, say, 5 or 6 sigma outlier in the relationship at redshift 0 becomes only a 2 or a 3 sigma outlier in the relationship at higher redshift, which makes them perhaps slightly easier to explain. Interestingly, as we've started to measure the stellar populations of these galaxies, we've been starting to find more evidence of this. So this is work from our brilliant PhD student, Louisa Buzzo. There's currently a paper in prep, but she's published similar work in her work earlier this year, where she's doing SED fitting for a large population of ultra-diffuse galaxies in field and group environments. So this is the stellar mass-metallicity relationship. Metallicity is on the y-axis, stellar mass is on the x-axis. You have the established relationship coming from Milky Way local group objects in this gray with shaded region. And we have ultra-diffuse galaxies plotted on this point, on this graph, the various colored points, as color-coded by their globular cluster richness. And in particular, the redder objects are the objects that we expect to lie off the stellar mass-halo mass relationship in this very massive dark matter-dominated region, because they have a lot of globular clusters, which likely indicates a large dark matter halo. And you'll actually see that there's this extra dotted line on this plot. This dashed line corresponds to the evolved stellar mass-metallicity relationship at redshift 2. In the early universe, there's less metals floating around, everything's got lower metallicity. And so these galaxies seem to be following this mass-metallicity relationship at higher redshift than what we see today. The other bit of evidence that these objects may have formed fast and early actually comes from their alpha abundances. So this is work from my collaborator Anna Ferry-Matau, co-author on the paper. And this is looking at the star formation histories of ultra-diffuse galaxies derived spectroscopically as color-coded by their alpha enhancement. And many of these galaxies that we seem to think are failed, they're the remnants of very early galaxy formation, seem to have star formation histories compatible with a very fast, very early formation in a single burst, where you get these extremely alpha-enhanced populations and low metallicities. And so we've starting to see evidence of this formation pathway from multiple different angles that aren't just dynamics, but also from the stellar population. So naturally, we wanted to, well, it was actually a talk I gave in ESO in Munich where I got asked the question, are these two classes distinct, or is it just a continuum of things that are forming early and failing early to things that are forming later? And so in order to investigate this, we asked our PhD student, Louisa Buzzo, have a think about what she could do to try and sort this out. And she came up with this k-means method, which I find really ingenious. So for those of you who don't know, k-means is a machine learning method where you put in a whole bunch of parameters, you normalize them on a scale of 0 to 1, and it tries to separate the galaxies into however many classes you would like, so as to maximize the difference in the means in the multi-parameter space, basically to try and get two groups as distinct as possible. Worth noting, you don't need to have the same number of galaxies in each group. It just simply tries to find two groups in the multi-parameter space. So Louisa gave it the ultra-diffuse galaxy stellar masses, their colors, their surface brightnesses, their mass-to-light ratios, their ages, their star formation timescales, their circularity, their axial ratio, their half-light radius, the distance from the dwarf mass-metallicity relationship, their number of globular clusters, their specific frequency of globular clusters, and the mass in the globular cluster system compared to the mass of stars in the galaxy itself, and performed this k-means analysis. And she found two very distinct classes. He found one class that's younger, forms slower, it's more elongated, it follows the dwarf mass metallicity relationship, and it has fewer globular clusters, which are more indicative of a dwarf galaxy. And this actually seems to be following this very dwarf-like formation pathway, which can be explained quite easily by current simulations. Excuse me. She also found the second class that's older, it forms faster, it's rounder, it's on the dwarf mass metallicity relationship at redshift 2, and it's got lots of globular clusters. And we would say that this is indicative of this failing dark matter halo. It's something that's formed early in the universe from a very quick burst of star formation, been catastrophically quenched. It has a high stellar mass high halo mass for its stellar mass, and a low metallicity indicative of this early formation. The other really cool thing about this is that with JWST coming online, we're actually starting to think we might be seeing some high redshift analogs as to what this galaxy could have looked like in the early universe. So this is a plot from Beiruzi et al. 2019, and thanks to my collaborator Aaron Romanowski for this slide inspiration, as to how dark matter halos grow stellar mass over the age of the universe. And in particular, if you focus on the halos of mass 10 to the 11, 10 to the 12, somewhere in between these two ranges, which we'd expect these failed dark matter UDGs to reside, and have a look at their the band of stellar masses where most of our observed UDGs reside, you can see that at a redshift of 2 or 3, these massive dark matter halos should have built up that stellar mass. And so if I was to just cover up the rest of this evolution and draw a horizontal line to the x-axis all the way to redshift 0, that's essentially the formation pathway we're going for. And so JWST has detected many objects at high redshift with large globular cluster systems. This is the sparkler here, and I've put stars on the plot for a few of the others: Cosmic Gems, Firefly Sparkle, and Max phone number. And these objects have very high fractions of their stellar mass contained within their globular cluster system, which is actually exactly what we're seeing for ultra-diffuse galaxies. I even think very visually, if you have a look at one of our ultra-diffuse galaxies with lots of the globular cluster system, globular clusters standing out across the stellar body, you might get a similar effect if you kind of try to reproduce the magnification that we're seeing in these clusters. But of course, this is PowerPoint, not science. And so just to really reinforce how very globular cluster rich these objects are, this is a plot of V-band luminosity versus the luminosity of the globular cluster system. Normal galaxies are plotted as the triangles. Coma cluster ultra-diffuse galaxies are plotted as the circles. The UDG I've been using throughout this talk to demonstrate globular cluster richness, 5846, is this star. You'll see it actually has 13% of its light contained within the globular cluster system. In these lenses that JWST is seeing of globular cluster formation at high redshift actually contain well in excess of 1%. Many of them contain even 50 or 60% of their light contained within their globular cluster system, which is very similar to what we're seeing for some of these ultra-diffuse galaxies. So we're left with this nice recipe to create a failed galaxy. You get fast star formation at high redshift, which leads you to more stars in your globular clusters. This also concentrates your supernova feedback, which drives out all your gas and a lot of mass and leads to creation of a dark matter core, perhaps. This can also lead to an increased susceptibility of tidal forces, but these two in concert likely lead to the large size we see in the ultra-diffuse galaxies today. And then you also have this idea of early quenching. You need this galaxy to form stars extremely quickly, but if the galaxy continues forming stars extremely quickly for the rest of the age of the universe, it's simply not the dwarf-like ultra-diffuse galaxy we see today. It's something more massive. You then get this quenching, which causes passive evolution in the stellar population, slowly fades with time, and you get this resulting low surface brightness. And this is the ultra-diffuse galaxy definition that we observe locally. Sorry, I'm just need a swig of water before I get to this plot. Okay. So many of the ultra-diffuse galaxies we observe locally are found in clusters. And so one of the natural things you may ask yourself with this failed galaxy sketchpad model is, because they're found in clusters, does this simply mean they formed at high redshift, were accreted onto the cluster, and then the cluster quenched them, and they've just been sitting in the cluster passively evolving for the rest of the age of the universe. And so in order to investigate this, we've created this plot. So it's a phase space diagram of the multiple clusters in which we found UDGs. It's the radius, which the projected radius from the center of the cluster, as normalized by the virial radius of the cluster. And then you also have the velocity difference from the center of the cluster as normalized by the velocity dispersion of the cluster. And you can actually color code this diagram based on the simulations of Rie et al. Based on the predominant infall time of different regions. So the way that this works is as the clusters grow, galaxies that are accreted later into the cluster are accreted into a more massive environment, and this causes them to lie on hotter, or this causes them to have more angular momentum and more energy, and so they reside in orbits that are further out in the cluster. And so if you're bound close into the center of the cluster, you tend to have infallen at much earlier times than those galaxies that reside further out. And so naively, if we expect these failed galaxy, very globular cluster rich things to have formed at high redshift and quenched by falling into the cluster, we actually probably expect most of them to be found in the relatively central region of the cluster. Conversely, if globular cluster poor things are just forming as normal dwarf galaxies infalling over the age of the cluster, we probably expect them to be found throughout the cluster. And so if we expect things with red borders, the very globular cluster rich things, to be found in the center, I'm actually not sure that's the trend we're seeing in this plot. Many of our very globular cluster rich ultra-diffuse galaxies seem to be found on orbits that put them further out in the cluster and consistent with infall at a much later time than could easily explain their quenching. And so this is just a little bit of a to be done. I still think we need to work on this and try and work out what is quenching these galaxies if it's not perhaps their infall into a cluster environment. So I just wanted to give a brief mention as to why I find this field so interesting. I really think that studying ultra-diffuse galaxies can help us solve some of the biggest problems facing our current understanding of galaxy formation. There's this lovely review by Laura Sales that was published, I think, 2 years ago, 1 year ago now, Baryonic Solutions and Challenges for Cosmological Models of Dwarf Galaxies. And so I think ultra-diffuse galaxies are starting to reveal a diversity of rotation curves. Certainly there's a very, many things in the H1 seem to be rotating very slowly for their stellar mass, and many of my galaxies seem to be rotating very quickly, well, seem to have a lot of dispersion support, which is equivalent to quick rotation for their stellar mass. There's a large diversity in dwarf sizes. These are some of the largest dwarf galaxies at their stellar mass, and so they contribute to this problem. I haven't spoken about it in this talk, but there's a large fraction of these ultra-diffuse galaxies that seem to be quiescent in the field, and explaining them is a problem that we're yet to tackle. My entire talk has been about the stellar mass-halo mass relationship, so I hope you understand how that's interesting. And I've presented some evidence that we might expect these galaxies to have dark matter cores, and so also understanding these galaxies will also help our understanding of this core cusp problem. If you've been interested in everything I've been talking about, I'm actually organizing a conference, 10 years ultra-diffuse galaxies, to take place in Benasque in Spain, which you're of course much closer to than I am, in August next year. I have Javier Roman, who I think may actually be at your institution. I'm unsure. I was looking at his website this morning, who's on my organizing committee. And if not, please feel free to reach out to me or Anna Ferry-Matau in the IAC. We're co-chairing the organizing committee. So I'll leave you with my conclusions. Spectroscopic UDGs are likely quite a biased bunch, poorly representative of the overall population, but we can still use them to perform interesting science. There's a QR code to my catalogue down the bottom there, and I can give you the link again if you would need it and would like to use it in your own science. Current dynamical mass evidence favors these very globular cluster rich ultra-diffuse galaxies residing in a core dark matter halo. They obey the globular cluster number halo mass relationship. They lie off the stellar mass halo mass relationship, and they have these very massive dark matter halos. They can only really be explained by this failing mechanism at high redshift. And evidence favors these being a distinct population within the UDG class. From this k-means analysis, our PhD student Luisa Buzo's done, and we're now starting to connect these objects beyond UDGs to see if the ultra-diffuse galaxy definition is necessary, or if maybe just these large globular cluster systems at fixed stellar mass is indicative of this formation pathway. So thank you very much for having me, and I'll answer any questions you may have.
Thank you very much, Jonah. Very interesting talk. So we have time for questions. You can unmute your microphone and ask your question if you wish.
Well, okay, I can ask questions.
Patricia, go ahead.
Hi, thanks for the talk, very interesting indeed. Yeah. Because I mean, there's a lot of stuff in there, so I probably missed something. But in the plot that you saw, well, I mean, then so in the stellar mass element relation, you saw several. But you saw the how do you obtain the stellar mass? I mean, it's like just with the luminosity or with the when you
For
saw the
those which we
dynamical
have,
mass in the X versus the dynamical between the radio dynamical and luminosity. I guess that you measure the velocity dispersion to get dynamical mass, and then you just with the luminosity you obtain approx for stellar mass.
yeah, so a lot of them, we have stellar population information, or if we don't have stellar population information, we have something like a G minus I color, which gives you a mass to light ratio, and a mass to light ratio of the stars. You have a rough estimate of the stellar masses.
Okay, thank you. I mean, I don't know, but you didn't show any error bars in the triangle, so I don't know how large the error bars are and what are the uncertainties, especially because there are low surface brightnesses. I don't know if there are systematics in the measurement notes.
Of course, I meant to say that early on in my talk. It's one of the lines I've just completely forgotten. Throughout my talk, I left off error bars from a lot of my plots because with the points so close together, it can overlap. Error bars on many of the points are of order 0.3 dex. And so in this stellar mass halo mass relationship, you can't really get the error bars to overlap the stellar mass halo mass relationship. And even if they did, it wouldn't really explain why you'd have 5 all at 1 sigma to the side.
Okay, thank you. Okay, great. And are the characteristics of the globular clusters like different or similar to other galaxies at the same mass? I mean, are they predominant? Are they all red, blue? I don't know. Are the characteristics of the globular clusters like what you would expect for the characteristics of the galaxies in terms of
the vast majority of the globular clusters for most of the galaxies seem to be blue and metal poor, which is exactly what we'd expect for normal dwarf galaxies. We have found a few cases where they seem to have very strange luminosities. So there's the famous case of DF2, DF4 in the 1052 group, but there's a lot of controversy surrounding them, and we're still trying to work out what's going on there. There's also a case of a galaxy in the outskirts of the, getting the name now, Pisces supercluster, the galaxy DG-SAT1, which seems to have much more luminous globular clusters than you'd expect, given its given the normal globular cluster luminosity function. And so we're even finding a few other cases in different environments. And so it seems like this universal globular cluster luminosity function that applies to almost all galaxies might be starting to break down on a somewhat regular basis for some of these ultra-diffuse galaxies, with you seeing more massive globular clusters than you'd expect. And we don't know.
Interesting, thank you. Just a quick one. Enrica, can I ask another one?
Yeah, go ahead.
Sorry. I mean, you saw, the globular clusters seem to be metal poor, all alpha enhanced, but did you measure ages as well?
We haven't measured, it's very hard to get spectra for the globular clusters, and so a lot of the time we can't get stellar populations for the globular clusters. For the few galaxies we do, they seem to be of a similar age to the actual body of the galaxy itself, and have similar metallicity, if not be slightly more metal poor than the galaxy.
You know, I was asking about the galaxies in fact, because you saw, the alpha iron that in the paper of Ferre Mateo and the paper of Anna, and then you saw also that they are metal poor. So I get those have a spectrum. I mean, I was asking about the galaxies themselves, because you didn't show any ages, I think, or maybe I missed it, but you saw the mass metallicity relation and the alpha Phi relation, but not the ages. So I guess
I guess you kind of get it from the star formation histories, where because the star formation peaks very early, it depends if you have a T90 or a T50 age or anything like that. But the vast majority of things we get that are these failed type seem to have ages that are 8 years plus.
Okay, Okay, thank you. And just like one, how easy it is, or how difficult, I don't know, how, to associate a globular cluster to a galaxy in a cluster? I mean, it is obvious always, or it is complicated? I don't know. I have no idea.
So with spectra, it's much easier. If they're at the same recessional velocity, you can do it. With photometry, it can be a little difficult, but usually the method you use is the same way that we use to identify the galaxy clusters themselves. It's just you have point sources spread throughout the cluster, and then you get a peak in the density profile associated with the galaxy. So if you were to measure a density profile of globular clusters or things with globular cluster-like colors from the center of the galaxy outwards, you'd see it falls off until it reaches the background of the cluster. And you can kind of measure that over density. And we'd say that those galaxies are statistically associated, or those globular clusters are statistically associated with the galaxy.
Okay. Okay, thank you very much. Very interesting stuff.
Yeah.
I'm done.
Thanks, Patricia. Any other questions? Well, I have a couple of questions as well. I think we can start with maybe a naive one. Due to the low super brightness of these galaxies, I was wondering how robust is the determination of the effective radius of this source, because it also affects the estimate of the mass as well.
No, very good question. So because a lot of these surface brightnesses are 24, 25 megs per arc second, you do need very deep imaging to get the surface brightnesses, but we're starting to get in the regime where many people are very good at getting deep images with, 3 sigma detection rates of 29, 30 megs per arc second. And so a lot of the time when we're measuring these surface brightnesses, we've specifically gone and taken a very deep image to get this, to get the surface brightness and to get the half-light radii. So I'd say for most of them, it's reasonably robust now.
Okay, thanks. And then the other one was, I was wondering if this kind of galaxy can host an AGN, and if in the evolution of these galaxies, what is the role of the AGN feedback or stellar feedback in the evolution of this object? And if in the simulation you show here in the last slide too, they include this parameter, this ingredient in their simulations.
So that's a really interesting question, and it's actually a little bit of my maybe not pet tip, but I think something we need to investigate more is the AGN. One of the big problems we'd have is that if an AGN is helping to quench these galaxies, because they don't have gas now, there's no AGN detectable, and there wouldn't really have been one for the last 8 gigayears. So I think it's an idea I think has a lot of merit as a way of quenching these if we were going to rule out clusters. But I'm not quite sure what the observational signatures of it would be today to test it. As for the second half of your question, these simulations, I'm unsure if fire implements AGN feedback, but I know in the Nihao run that was done, they didn't have AGN feedback. And there's some recent work by their PhD, by Ariana de Cintio's PhD student, Elena, I'm forgetting her last name, who added AGN to normal dwarf galaxies. So they did a run of their Nihao simulation with just normal descriptions, and then they added AGN and saw how that changed it. It's a very interesting paper. And on average, they found that for many galaxies, it actually slightly suppressed star formation over the age of the galaxy. And so I do think it is possible, but I'm just a little stuck as to what the signature would be today of an AGN in these galaxies, or of AGN quenching at high redshift in these galaxies, if the AGN is no longer active.
Okay, thank you. And in one of your previous slides, when you showed the result by boson, the dichotomy you found between different kind of globular clusters, these two type of galaxies, do they belong to the field or cluster group, or they are mixed?
A little bit of the problem we have is that we've got a lot of very good measurements of the globular cluster systems of things in clusters, because we already had archival HST imaging that just happened to have these galaxies in them. But we haven't been as successful at getting follow-up imaging of things in the field. I would say, though, the early indications are that it seems there may be a slight bias to these things being in clusters. Excuse me. And so I've been talking with some simulator friends about what that may mean, and one of the ideas is simply that in a protocluster environment, you might have more gas available, just ever so slightly more than in a protofield environment, which will preferentially allow you to have these large starbursts that would be needed to form these galaxies. But overall, I still think it's a bit of an open question beyond them being slightly favored to be being found in a cluster environment today.
Okay, thank you very much. Any other questions? Well, if not, I think we can thank the speaker again. Thank you very much, Jonah. I really enjoyed your talk. And thank you very much for joining us. So,
Thank you very much for having me. Enjoy the rest of your Fridays and enjoy your weekends, everyone.
Thank you. Have a nice weekend, you too. Thanks.
Bye.
Bye, everyone. Bye.
Great talk.
Bye. Thank you.